Okay, welcome back to chemistry. So I'm asking you to be able to write out reactions for alpha, beta, and gamma decay reactions that can happen. So as a reminder, alpha is a helium nucleus. I'll show you what it looks like in just a minute. It doesn't penetrate very far, so you can block it with paper, but it's a very common type of radiation. Is found in things like smoke detectors have americium, which decays through alpha particle decay. Beta particle is an electron that comes screaming out of the nucleus, so we're converting a neutron into a proton by kicking an electron out of there. Go back and look at the video that explains that before. So we're going to get a beta particle. It's smaller, so it doesn't have as much mass, but it has more penetrating power, so this will go through paper but not through aluminum. And they're used for, I used to use beta particles when I was doing research, so it's an easier thing to work with, it's not quite as dangerous, and it's generally have shorter half-life, so it's something that's easier to work with. Lastly, gamma particles. Gamma particles are just energy, so we have a different way of representing that, and they have the most penetrating power, so they're most dangerous. All of those that they get blocked by lead, but not aluminum or paper. So they're used for a variety of things, including irradiation of food. So and sterilization of equipment. So let me remind you what this looks like. So I'm going to ask you to be able to write out and interpret these reactions that are coming up. So brief reminder. So if I start with something like polonium-209, that this can go through alpha decay. So what this means, I'm going to start with that, right? So this is my reactant on the left side and my products on the right side. I'm going to end up with an alpha particle. An alpha particle is a helium nucleus. So this is one way of writing it. Sometimes we write it as a 4-2 with an alpha character. Either one's fine. I just use the helium nucleus because it makes more sense to me. And then I'm going to have some stuff left over, but here we go. So we have two conservations that we're going to worry about. We're going to have conservation of mass. So this number on top is the mass. So I start out with a mass of 209. 4 of it gets thrown out of the nucleus, so I must be left with the remainder. Grab a calculator or do the math in your head. You'll end up with 205. The bottom number represents the charge. And be careful how I say this. So this is a charge. So I start with a charge of positive 84. 2 of those get flung out in the alpha particle, so I must be left with 82. Now I'm going to go to the periodic table and look up what is element number 82. Well, here we go. 81, 82. That's going to be lead. So I'm going to write down lead as my, there you go. I'm going to write down lead as the thing that I get, right? So this is what you want to end up with. So again, be careful. So notice that my mass is balanced between my reactants and products, and my charge is also balanced between reactants and products. A common reaction that we'll take a look at a bit is one that goes through beta decay. So if I take carbon-14, so again, carbon-14, so it has a mass of 14, it has 6 protons because it's carbon, so it has to. This is going to decay through a beta particle, so we're going to be careful about this. So a beta particle has a mass of 0 and a charge of -1. Remember, this is an electron that comes out of the nucleus. What happens, I start with a neutron, and I can think of a neutron as having both a positive and negative charge in there. I shoot out the negative charge, and now I'm left with a proton. Weird. But don't worry about it. So this is what I'm going to do, is I'm going to worry about the same two things. I'm going to balance the mass on top. So I started with 14. An electron really has negligible masses a little bit, but we're not going to worry about it. So I'm left with the same mass of 14. I'm going to balance the charge and be careful. So I start with a charge of +6. I need the charge on my reactant side to add up to +6. This is -1, so this needs to be 7. I've increased the number of protons. And when I look this up, I'll find out this is nitrogen, and this is carbon-14, how this decays. A really common reaction that we use for radio dating things. I look at the ratio of carbon-14 and carbon-12. So again, this is a beta particle that's being ejected. So importantly, this is an electron that's coming from the nucleus. It didn't exist before as a separate electron, and it's coming from the nucleus, and it leaves me with the nitrogen. So I'm going to ask you to write and interpret these reactions. So I might give you, I don't know, I might not tell you this is carbon and ask you to figure it out. I might not give you this. I might ask you to figure out what particle it is, or I might not give you some part of this and ask you to figure out the rest of it. So that's what you'll need to be able to do by the end of the week. So we'll give you a chance to get some practice with that. Hope that helps. Talk to you soon. Bye.